Well, hello everyone. We are dealing now with our final chapter, chapter 9. Excuse my voice if it disappears occasionally. Well, essentially what we're going to work with is the topic of differential equations. And first section is modelling with differential equations. But before we get started with that, let me give you a little bit of a background. And let's start with a definition. A differential equation almost always called dif-eq or DE, differential equation, is an equation that contains a derivative. It's pretty obvious, I would think, with its name. And differential equations are like the foundation of a lot of physics theory and modelling in particular. Modelling is creating formula to describe some kind of natural phenomena that you can observe. And so examples of a differential equation could simply be something like the rate of change of population with time is 0.2 times p. You could get a differential equation like x dy by dx plus 5y equals 3. That would be a differential equation. You could get one dz by dt is equal to dw by dt plus t. These all are examples of differential equations. And these particular ones are called first order differential equations. And they get that name because the highest derivative is the first derivative. So they all contain at most a first derivative. And most of our job is going to be in solving a differential equation. Now, that's not the only kind of differential equation. There's no reason why you couldn't, for instance, have d squared y over dx squared plus x dy by dx plus 3y equals 0, or d squared z over dx squared equals dz over dy plus a z. That would be a differential equation with quite a messy type. We would consider these differential equations to be second order. Now, it's pretty obvious that they're called second order because they contain second derivatives and third derivatives and 10th derivatives. But for the most part, we'll deal with first order differential equations. Differential equations are so important that if you look at the courses at Olympic College and even at university, I'm sure, you'll find that we have an entire class devoted to nothing but differential equations called Diff-Eq 1, Differential Equations 1, and then a second class devoted to differential equations called Diff-Eq 2. So you can imagine 2 full classes at the end only on solving differential equations and creating models that use them is pretty impressive. If you become an engineer Your bread and butter work will be dealing with differential equations. That's the kind of method, technique that is used to solve many problems. You create a differential equation that describes the situation, and then you try and, one way or another, solve that differential equation, and that allows you to gain insight into what's going on. So that's the kind of intro. Let's see where we're going to go to now. Well, let's talk about how you can create a differential equation. Now, to do that, we need to think a little bit about the way that we describe relationships. In particular, whenever you see things like the rate of change. I want you to think the derivative of something. And it's usually some variable with respect to time. But it can be others. So for instance, if you see the rate of change of a population, let's see, varies by 0.1, the value of the population. I would create a differential equation, something like this. Let's call P the population. So the rate of change is that guy. And you're telling me it's 0.1, so the rate of change, the derivative, is 0.1 times the population. And that would essentially be our first order differential equation. And then later on, we'll show you how to solve those things. So let's have a look at some of the homework questions. It's much easier, I think, when you can see ones, especially the way they end up writing them in the web assign for us to do that. So click off this guy and I'll go, yeah. So we're being asked to write a differential equation that models the given situation. The stating the rate of change with respect to time. Use K for the proportionality constant. So if they don't tell you that it varies by 0.1, they just say it varies according to the value of the population, then you replace the unknown with a K. So the rate of change of the radius R of a tree trunk is inversely proportional to the radius. Now, if you know anything about physics, isn't inverse 1 over the thing? So we don't know that the top number for sure is 1. So we do K over R. That was it. The rate of change of velocity V of a following body is constant. Right. Put in K. That's all that you're told. The rate of change is a constant. For a car with a maximum velocity of m, the rate of change of velocity, which is this thing, is proportional to the difference between m and v. So the proportion, the difference between m and v. So it's relatively easy in using the language of physics, which is basically inverse and directly proportion, right? To create a differential equation without too much effort. Now, once you create that, you can then go on and look at the details of, well, if you supply me some values, especially for K and M, we can then go on and solve this differential equation and create a formula for the velocity at any time t, or the velocity in this case as well, or what the radius of this circle would be at any given, this tree trunk, I guess, would be at any given point in time. So let's have a look at the fourth and last one at this type. So when an advertising company has a campaign for a new product is introduced into a city with a fixed population n, okay, n's a constant, the rate of change of the number y of individuals who've heard the product at time t is proportional. So proportional, okay. The number of individuals in the population who have not yet heard about it. Now, y is the number of individuals in the population. The number who haven't heard it then is the entire population, take away those who've heard about it. And that's that one done. Now, the next group of questions are, here is a possible solution to a given differential equation. What we're going to look at is, how do we check that it is in fact a solution? So we're not creating the solution. All we're going to do is check that the one that they gave us actually works. So in question 5, the differential equation y dashed plus 2y should equal 2e to the x. And they're saying that this here is a possible solution. And we have to check whether or not it works. So all I'm going to do is I'm going to take this fella here. I'm going to find its first derivative. I'm then going to add 2 of these. And if it equals this guy, then it's a solution. And if it doesn't equal, it's not. So let's see, y dashed is 2/3 e to the x. Differentiate that, you get negative 2 e to the negative 2x. That's fine. Now, I'm just going to make it a little column. So I'm going to add 2y. So 2 of these guys get you 4/3 of this guy plus 2 of this guy. Now, if we add them together, what do I get? Well, that and that gets me 6/3, so I get 2e to the x, and that cancels, and it's a yes. Now, here's one of the differences in differential equations that aren't that common or even realized really in normal equations that you've previously dealt with. Yes, this is a solution to that differential equation, but it's not the only solution. There can, in fact, be, in many cases, an infinite number of solutions. And these families of solutions, right, this whole bunch of solutions all work, are very often called the general solutions. This is just one particular example, so we would call this a particular solution. Well, the next question is pretty much the same idea. This is question 6. In question 6, the differential equation we've got is this guy plus that equals 7 sin x. And we are given 4 choices. and it says select all that apply. Now that could mean that there's only one solution. Of course, it could mean that 2, 3, or all 4 of them are solutions. So you can't just, pick one, and if it works, say, oh, well, that's it, I've got the answer, I can move on, because there may be another answer as well. And so there's really no shortcut except to test all of them. I don't want to test all 4 because we have work to do, but for no particular reason, and I honestly don't know if this one is going to solve or not, I'm going to try that one out. So let's test this one. It's the second one. Well, there's y. The differential equation needs 2 derivatives plus the y, and it should equal that if it works. So first derivative is differentiate that. The second derivative is differentiate that. You want me to add a y to it. Okay. And I'm either really lucky or really unlucky that they add up to 0. But shouldn't they add up to 7 sin x? So this guy here is not a solution. But there are 3 others that may well be. Now, next question is a little bit different from that. Here we have a differential equation. It's called a logistic population model, if you're interested in its name. It's 1.4 p, 1 take away p over 4400. Now they're asking us in question 7, for what values of p is the population increasing? So p is the population, and when is it increasing? Well, it's increasing when the derivative is 0. I'm going to make an assumption, which is, I think, pretty obvious, that whatever the solution is, we can only use values of p that are positive. So I'm looking at 1.4p times 1 take away this guy. So if we're only going to have positive values of p, 1.4, let's put it in all its glory here, the entire equation. 1.4p is guaranteed to be positive. So if I want this to be positive, then I have to choose only values of p that make this positive. So now we're trying to solve, when is this positive? Well, this is going to be positive when this guy is less than 1. Would you agree? 1 take away less than 1 gives you a positive answer. And when is this going to be less than 1? When p is less than 4400. So 0 to there. 0, 4, 4, 0, 0. And that is our answer for question 9. Now, when it asks in part B for when is the population decreasing. That's going to happen when the derivative is less than 0. P is still going to be greater than 0. You can't really have a population of less than none, right? So that's why that restriction is kind of guaranteed. So I am trying to find out how to make this fella. Like I wanted to make this guy here positive. I want to make this thing negative. Well, because P is greater than 0, this piece is always positive. So we really only need to focus on making that negative. And that's going to be negative when this is bigger than 1. And this is going to be bigger than 1 when P is bigger than that guy. So any value of P from 4400 onwards in interval notation would work. And then they ask the last one, what's called equilibrium system. Equilibrium solutions. Now they are going to happen when the rate change is 0. Essentially when the population is balanced. No increase, no decrease, levels up. So we're trying to solve when is this equal to 0? Well, the first one's pretty easy. P equals 0. The second one is, well, relatively easy, 4400. Now, if you start off with nobody, you're just going to continue to have no population. Evidently, in this model, if you start off with this number, or eventually reach this number, which is more likely, the population reaches equilibrium. Although it's a relatively simple differential equation, the power in this is that it allows us to model population growth in a much more realistic way. When you did exponential growth, they always looked like that. And they were good for 4, 5, 6, 7, 8, 9 years. But eventually, if you used the model, it was useless for 100 years. Everybody in the world ends up living in one place. What typically happens when you graph this kind of model is it goes like this and then it kind of levels off. In this case, at 4400. And so the balance of nature, if you have an island with rabbits and foxes and all kinds of creatures and they all do what nature intends them to do and you keep out the road, they kind of find their own natural level, their equilibrium solution. And the rabbits, let's say 4,400 rabbits, is the optimum number that will work on the island. If you get too many rabbits, they eat too much food, they die because they starve. A few survive. The few that survive, it gives the island a chance for the vegetation to grow back. Eventually, the rabbit population grows, the vegetation grows, they balance. It's much more natural, of course, to have predators on the island. And the predators and the prey have this uneasy alliance where they basically keep each other in balance, right? If there's a lot of rabbits, more foxes get born, and more foxes eat more rabbits. And then if there's too many foxes and not enough rabbits, the foxes die off and the rabbits have a better chance of living because there's fewer foxes to catch them, and equilibrium starts all over again. It's found to be very resilient as a population growth model, much better than it just shoots off to infinity if you left it. A very, very cool model. And logistic model is its name, if you want to find more information about it. Question 9. Show that every member of the family, well, actually, let me show you this question. That way we could do it together. Okay. So it says, show that every member of this family. So what you have here is an equation with a thing called an RPG constant. It's like an arbitrary constant in integration. And we just show the solution to this differential equation. So you have y is this guy. And now you've got its derivative. And basically what you can see here is f dash g plus f of g dashed, all that good stuff. So let's see what we get if you go and you, excuse me. I'm just looking at this and finding out the order they've written. It's a bit weird for my brain, but never mind. Okay, so I'm trying to find the first derivative of this thing, and the way I'm looking at it, it's 2 log x plus c over x. So it's basically f over j. And I'm just a little, oh, I see. What a weird way to do things. We're calling, that does not make sense. See what the heck they're doing here. It looks like they're doing the 2 and integrating it to get x, which is not what you need to do. So let's get by that guy. Right, here we go. So what have they done? Okay, it's just the way they've written it. I call it f dash g minus f of g dashed over g squared, and they do their g's and f's the wrong way around. These Americans are strange creatures. Never mind. This is the quotient rule as I thought it should be. It was just the way they wrote it confused me. So if you take the top guy in column F and you take the bottom guy in column G, then you can see that what you've got here is well, they've rearranged it as well. So essentially 2 over 1 over x times x, take away, and if you take the other guy, you get that fella. That is a rather stupid way of doing it, to be absolutely honest. Could have done that a lot cleaner, but it is what it is. It is a quotient. Well, it's just the way they've written it. Looks weird to me. And once you know that derivative, which is this, that guy there fits in here. Then all they're doing next is x squared times this guy plus x times the original function. And then they're tidying it up, and the whole thing comes out to 2. So it's a solution. So it's basically check that this solves that differential equation. And they did it in a rather clunky way, but I guess it works. It then says illustrate part A by graphing several members of it. So what they want you to do here is take this fella here and do, I don't know, 2 log x plus 1 over x, 2 log x plus 5 over x, 2 log x over x, and maybe 2 log x minus 3 over x. And when you draw a whole family of them, one of these comes out. What that tells us is quite interesting. For me, I think it's fascinating that when you have a family of solutions, right? So any value of c here will give you a solution to that differential equation. So you could have any one of an infinite number of solutions, but they are a family because they all kind of look the same with one exception, right? That little guy there will be a different number. And when you plot them all, what you get very often, I think of them as like models of things like currents. Can you imagine a current, I know, a jet of water, or maybe electrical particles hitting some kind of field, and they get deflected downwards or upwards depending on what's going on. One of these, evidently it's that one, is what all the family look like. Now they then go on and say, find a solution that satisfies the initial condition y1 is 4. So I'm going to show you how you would get that answer. So we have y equals 2 log x plus c over x. And we're going to solve for this and find a particular solution, just one of those many curves. And the one we want is the one that has the property that, let's read it out again, that y of 1 equals 4. Y of 1 equals 4 is basically saying y equals 4 when x equals 1. That's how you read that. So y equals 4 when x equals 1. Well, 2 log of 1 is 2 logs. Well, 2 times 0 is 0, so you get c over 1. So well, that wasn't that hard to do. So the particular solution to this differential equation has a 4 there. And if you have a slightly different condition, that y of 4 equals 1, so you see kind of swap places here, that means when x is 4, y is 1. What does that look like? Well, 2 log x plus c over x becomes 2 log 4 plus c over 4 equals 1. We'll cross multiply. So 4, take away 2 log 4, c. So I now replace that c with this, and we're finished. So it's 2 log x plus a 4 minus a 2 log 4 over x. And call it good. I could actually tidy that up, but I'm not bother. Now the next one is very similar, but I'm not going to show you their way of doing it because it'll just confuse me. Starts off by giving you a differential equation that looks like that. And it says to you, what can you say about the solution? Well, I can tell you that its derivative has to be negative. You may say, well, how do I know that? No matter what value of y you pick, this will always be positive. And this is a fixed value. So together, it's negative. The only exception would be that when y is 0, the answer, by that I mean the derivative, would be 0. And that ends up being the third circle down, at least in mine. Now we're given a general solution. And we're being asked to test that that is the solution to this guy. So I'm going to rewrite this guy like that. And now I can differentiate him. Well, y dashed is going to be multiplied by the power and reduce the power by 1. And then make it look pretty. And I'm going to find negative 1/5 of y squared. So it's going to be negative 1/5 of this thing squared. And that's 25, partially cancels with that, so I get a negative 5. And that guy squared gets me x plus c squared, and would you agree? They are equal. So it works. It's a solution. And that's the answer to B. Question C gives you a number of choices and asks you for another solution to this differential equation that does not fit this formula. And really boring solution is that one. I believe that's the only one that you can check for others. Oh, they give you ones to check, so basically you go through them all and find out if there's others. And then they finish off with the classic. Right, here's your guy. You've been told y of 0 is nothing 0.2, and you have to find the particular solution to the differential equation of this form that that's true for. So what does that say? That tells me that x equals 0 and y would be 0.2. So I'm going to go 0.2 is 5, 0 plus c. So 0.2c is 5. So that makes 5. That makes c, I should say, 25. Plug 25 in there, and you're finished. And that is us finished for this section. Thank you for suffering your way through me coughing.